All right, so we are talking about falsification and how falsification plays an essential role in machine learning. And we're going to try to understand that using our good old friend, the growth function. So let us assume we have this hypothesis set H that shatters this data set, right? And of course, let us assume this is like some randomly generated data set and it's really complex. And also H is extremely complex. So do not be surprised if you are able to fit the data because H is so complex that there is no way that it won't shatter any randomly generated data, right? Another way to think about it is like um, this argument that we've been giving that simpler has a better chance of being right um, goes as follows. Like it is like this is how this is being described is that let's say we are trying to fit a hypothesis to this like data that's given to us, some randomly generated data, and let's say the outcome is binary, the y's are binary. So there will be very few simple hypotheses than the complex ones. The number of these simple hypotheses will be less than the complex ones because with complex hypotheses, you can get as complex as you would like them to go. And then there would be enough of them to shatter any given data set, like any data you can shatter it, right? So like any given random data set. So therefore, like fitting the data does not mean much because anyways you'll be able to fit it, right? And so if in fact, like the opposite, like if you fit this data set with a simpler model with very few hypotheses, then that is surprising, right? Then that really means something that's significant. And so that's what we are after. So another quantifiable way of saying why this is significant is that we're looking at this one. Let's assume that H is another hypothesis set that does not shatter this data set, right? And that let's say the data is uniformly distributed. And if you think about it, because this is a simpler hypothesis set, we can say something about the growth function for that hypothesis set, right? So maybe this M sub H of n, the number of dichotomies H can implement, is not that complex, right? So that means the number of dichotomies that H can implement is this. And so the probability that H can implement these dichotomies is M sub H of n divided by the total number, right? And the probability of falsification is going to be 1 minus that total number, right? And so in this case, if this is a simpler hypothesis, that means my M sub H of n is small. And that also means that this thing is small. And so my probability of falsification is huge, right? It's high, almost 1. So how does that help us? Well, this is like quantifiably, we are saying that simpler is better because although the probability of this falsification was huge, but we were still able to fit my data. Or basically, you could have falsified, but still your model fits so well. And that the fact you didn't falsify is significant. That's the idea here. And that's why we want to be simple, right? So good fit is surprising with simple hypotheses. And that is why it's significant. Okay, so you can falsify, but you didn't, and so that's a good result, essentially. Okay, so this was about falsification and keeping simple and about Occam's razor. And so learning from data in general, we should opt for a simpler fit than possible, right? And our goal is to get basically E out small, which means it's not necessary that we get E in equal to 0. In learning, learning is essentially taking this Occam's principle like a level ahead instead, right? It's taking a level ahead because like what Occam said is that you fit like a simpler fit is good enough, but in like learning we are saying an imperfect fit is fine. Like I can settle for E in not equal to 0, but like maybe small, but then the relationship between E in and E out should be tight, right? That's what we are after in learning. And so that's why we are taking this Occam's principle to the next level in learning. So basically what we are saying is we may go even simpler. That is, we are ready to settle with an imperfect fit, right? And then using a simpler model over a complex one due to the price we may pay for complexity, right? So machine learning, again, is the next level of Occam's principle. And because we can quantify the relationship between E in and E out, that's what we've been doing until now. And so based on that idea, we may even go for an imperfect fit. That's fine as long as we are not going into the complex region because we know the negatives that come in with that. All right. To end this idea of Occam's razor, we will look at this nice example, which is exercise 5.2 in the textbook. And what we're looking at is there is some football oracle, I would say. And why is this person a football oracle? Let's say I receive a postcard from somebody that tells me that home team will win the Monday night football game. Well, it looks like some random postcard that somebody sent me, and so just like I threw it away, right? And then this was like Monday 1, right? So Monday 1. And then the next week, Monday 2, right, I again receive a similar kind of postcard that tells me that the away team, let's say, is going to win, right? And again, okay, that's fine. It looks like some, again, a random postcard that I received, and so just like throw it away. And suppose that I keep receiving these postcards 5 weeks in a row, right? And then the outcome always, like the prediction of these postcards, prediction always matches the outcome, always. And so after like the fifth Monday, I'm like a little bit keen, to kind of think about it, that like this prediction is always matching the outcome. So maybe this person is a football oracle, and like maybe they are excellent at predicting. They know everything what's going to happen. And so what happens, like after the fifth, like the sixth week, I receive a postcard saying that if you want to know the prediction for this week, then you have to make a payment of $50. Okay, so here I am, like I'm stumped because should I be paying this or not? So that's the question. Should I be willing to pay? Because until now, what has happened is that I've seen that the prediction always matched the outcome. So maybe they're making this like perfect prediction, right? And so, am I willing to pay $50 for that or not? Okay. So before that, as like people who are into machine learning and as people who are trying to understand what's going on with predictions, we'd like to understand what this person did. And what they did was something like this. Okay. So this is my data. So every day, day 1, day 2, day 3, Monday 1, Monday 2, Monday 3, and all. These are my data points, right? So these are my data points. And I am, like, this is me, and I am one of the hypotheses. Okay, so what exactly is this hypothesis? What this person did was on day 1, they sent this postcard, and there are only two outcomes. If you think about it, there are only two outcomes, either the home team wins or loses, right? And so what they did was like randomly picked 16 people. Yeah, randomly picked 16 people, sent half of them as a win and the rest of them as a lose for the home team, right? So that's what they did. And then based on the actual outcome, they saw that for these 8 people, it turned out for these like 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, that's correct. I just wanted to make sure that we have the correct count. So for these 16 people, so initially they sent for 2 to the 5. That's 32. Yeah, that makes sense, right? The maximum number possible. And then for these 16 people, it turned out to be true, obviously, because half of them would be true. And so they picked those. And then the next week, they sent half as a win and half as a lose. And they kept doing that pattern until they got that one person, which is like, believe it or not, it was me. And they got all of the predictions right. So not really, they weren't really predicting, but these were all the hypotheses that they had. And obviously one of them is going to match the actual outcome. And so, believe it or not, I believed that this person is a football oracle indeed, and they are able to like predict perfectly. And so this is what was happening behind the scenes, right? They had this like 2 to the 5 hypotheses, and eventually this is what happened here. And if you think about it, like, of course, like my in sample error here is 0 because this is like a perfect match. But then we have to think what's going on behind the scenes, right? So after like predicting so much, think about the cost that literally went into achieving this, right? So maybe think of like how many letters this person must be sending in these 5 weeks. If the cost of printing and mailing of every letter is like some, I don't know, $1 or like maybe 0.5 cents, how much would this person make if like this sender, that like the recipient rather, which is me, is willing to pay $50, right? So if the amount of cost, like the cost that they put in to kind of do all this, right, have all the hypotheses and then test them and all of that, and so if that was greater than $50, right, then if I'm willing to pay $50, then obviously they don't make anything. But then if it was less than $50, then they will make something at least out of this, right? So the idea being, like generally speaking, the idea being here is that um, this was like the max this hypothesis could go, and so one of them has to kind of fit the data that's there. And so as like people who are who understand the relationship between E in and E out, we also have to see the complexity that accompanies this like E in order to predict E out, so whether they will be predicting correctly or not going forward, and so on, right? So here, whether we'll be willing to pay that much or not from the perspective of the person who's actually sending me those postcards is really in terms of like how much cost went in to make this E in really equal to zero. So that was like an example that kind of demonstrates the relationship between learning and the choice of the hypotheses and how complex things can get and so on. So one question that is left for everybody to think about, to ponder is, can you relate this situation directly to the growth function and the credibility of fitting the data, and how? Right? So I'm leaving that question to you because we've talked about it so many times and this is like a real world example kind of demonstrating that. All right. So that's the first learning principle, the Occam's razor, and we are just finishing that. And now we are beginning to talk about something that's known as sampling bias, another issue when working with machine learning models. In general, in definition, if the data is sampled in a biased way, then learning will produce a biased outcome. And we look at what that means. Okay, this here nice picture actually shows a high-level idea of what this means. So here a selection of people or animals is being made, and for like the person who's making the choice is saying, for a fair selection, everybody has to take the same exam. So everybody needs to climb the tree, and you already know before actually this test happens, the monkey is the only one who's going to win or make any progress rather. So this is the fundamental idea of sampling bias. All right, in terms of machine learning, what does sampling bias means? We are looking at this like example from 1948 US presidential elections, where a very well-known newspaper, which is like the Chicago Daily Tribune, they happened to like they went ahead and like even before the actual results were declared, they went ahead and they declared on the election night that a day before the results rather, that Dewey is going to win and Truman is going to lose, right? So they came up with this, and they just like wanted to show off that they are so ahead in whatever technology they are using to predict things, and this was a major headline, right? However, believe it or not, when the actual votes were counted, this was the result, right? So, and this is here, in this picture, you can see this is actually Truman smiling and holding this because Dewey actually lost, right? So, believe it or not, this is the true outcome. So, what happened with the prediction? Was it something with the statistical analysis, or was it a statistical anomaly? Or maybe the newspaper was just unlucky? What really happened? Like, what went wrong here? Well, it turned out that the way this newspaper went ahead and collected the data, right, was that on election night, they carried out a telephone poll. So they did a telephone poll, and in that poll, they asked people whom they voted for. So that was like, that's what happened. So this is like an experiment that was doomed from the very beginning, regardless of the size of the data or the sample that they're using. And even if this experiment is repeated, the result will still be the same. Why? Well, in 1948, right, telephone wasn't as common as you can tell, and they were expensive as well. So whoever like gave their like participated in the polls was basically they belonged to an elite group, right, and then that elite group favored Dewey much more than the average voter did. And so because the newspaper did its poll by telephone, right, and the telephone were mostly owned by rich people, it inadvertently use this in-sample distribution that was different from the out-of-sample for which they were making the prediction, right? And so this goes back to one of the basic principles of learning. And when we were looking at the VC analysis, we looked at the theory, and then we said, like, one of the assumptions was that the data set is generated from the same distribution, and then the final hypothesis is should be tested on that, right? So in practice, we can encounter such data sets where they are not generated under those ideal conditions. So there's something that's like off between like where you're testing versus where you're collecting the data from. And that is going to implicitly produce this sampling bias that we just saw in this like real world example. All right. So what is sampling bias in learning? By definition, if the data is sampled in a biased way, like we saw, learning will produce a similarly biased outcome, because learning is nothing but like we learn from the data, right? So we are making all our predictions based on the data that we have, right? And so we have to make sure that the training and the test distributions are the same. Basically, when we started with the bin model, if you remember, you cannot draw a sample from one bin and make claims about another bin. For example, I cannot sample people from, let's say, the United Kingdom and then make predictions about who's going to be the president in the United States. So that's like a sampling bias. My sample is totally like from a different bin, right? And that's something that's creating issues with my prediction. All right, so that was the example for sampling bias. Another sort of subtle, like again, this is also sampling bias, but this is introduced not because of the like we explicitly are doing something to it, and this is like the credit analysis problem that we've been looking since I think lecture 2 or so. And so here what's happening is, in case of this like data that we have for credit analysis, right? We have to determine based on whatever we have information we have of some bank customers whether we should be approving or denying credit, and we have looked at it a lot, right? And the small issue with this here is that we are trying to predict whether this person is going to default their credit or not based on the people who have defaulted or not. But then there is data only for approved customers, if you think about it, right? So the bank has created this training set from the database of previous customers and how they performed for this bank. And so it has excluded all those people who applied, right, and were denied for whatever reason, because like the data set like started forming maybe because of human intervention and people were collecting that data, right? And so they were denied, and we don't know how they would have done if they were in the system, right? So now like we'll use this data on approved customers only, and then we'll also make predictions about these people who are again going to apply and whether they'll be denied or not, right? So this is like like there is no way out if you think about it for the bank customers. So future applicants will come in from mixed population, and then there will be people who rejected in the past. So the test set actually comes from a distribution that's different from my training set, from where I based my model on. So in a scenario like this, you cannot do much about it, right? Nothing can be done except that maybe you can acknowledge and like put this word of caution on your predictions. Like when you predict something, like have this word of caution that this is the limitation of your model. This is the limitation of your prediction, and so on, right? So whether you believe it or not, sampling bias is more common than you can think, and a lot of bias is introduced in like human intervention. For example, one nice example that the book gives is let's say a Wall Street firm who wants to develop an automated trading system. So they usually will take data sets when the market was behaving really well, and so what happens when the like what happened to the bad examples, right? And so there is that bias trap that you get into. All right, so sampling bias has been called selection bias in statistics. So sometimes when you come across the word selection bias and you've taken some statistical classes, we have also talked about a little bit of that, I think, in one of the lectures. So the bias can arise in, like, first of all, the bias arises in how the data was sampled. And then in the context of learning, like maybe selection of a final hypothesis from the learning model based on that data. So it's like a combination of both. All right, so that was sampling bias. And then before we end this section, I just wanted to talk a little bit about extrapolation. And what is this extrapolation and why it shouldn't be done? Because again, it is kind of introducing this idea of bias, like this test from one bin and train on another bin, and so on. So let's see, like, let's look at a quick example. Let me assume that there is this like data, one-dimensional data, and then I have this outcome y. And let's say the data is distributed something like this, right? And I have lots of data. And let us assume that I, just by like the fact that I know that simple models do well, I just like fitted a line here within this data, right? And then my test point comes in, right? And so my test point is somewhere, I don't know, a test point, or maybe I'm like testing somewhere, or maybe I'm not like even testing. I just want to predict for like some x here, right? So let's say this is like xn. I just really want to predict, and it's not on this line is what my point is, right? It's not on this line, it's beyond that. And so I wanted to predict for that. And so based on my like whatever ideas I have about it somewhere here, I would just like go ahead and like extrapolate, right? Extrapolate means I'm just like going to extend this line from my linear regression output. And I'll say, yeah, this is the value for y, and so this is my prediction, right? And this is like common. But there are that some issues that exist with extrapolation that we have to first of all keep in mind. I would say, and it's not the case that it will never be like this. But sometimes what happens is that here again we are making this mistake, right? Is that we are sampling from one bin. So if you think about learning in general, it is about interpolation. It's not about extrapolation, right? So maybe this point that we thought that will have the y value of this, maybe the y value was this, because maybe the target function was something like this, right? And so maybe the predicted value was this. And so like the actual value was this rather, right? So the issue here is that we are relating, like we are sampling from one bin and relating it to another, trying to predict with, like we are trying to predict outside of the bin. So whenever we try to extrapolate, we have to take that with a like a pinch of salt, I would say, and be like extra careful, because we are asking for a prediction that is not representative of the data, right? So this is not a representative of the data. So I'm not saying that this is going to go wrong all the time, but that bias may be introduced at times when you're trying to extrapolate, because extrapolation is hard, right? And it is hard because of this bin model coming into picture. All right, so in the field of learning from data, sampling bias is something that we need to be extra careful about. And in the next video, I will begin to talk about something that's known as data snooping. Again, we've looked at that before, but let's discuss that even further.